we come to estimation. Estimation is another inferential technique, so rejection region, p-value method, and now estimation. And it can be used in conjunction with hypothesis testing. It's very important actually to have both in your papers, or when you read, you have to look at the confidence interval. It means, estimation means using sample statistic to estimate the population parameters. And there are two different types of estimates. It's a point estimate and interval estimate. Point estimate, when you take a sample and get the mean of that sample, that's the point estimate for the population mean. So you use a single number or your estimate of an unknown quantity. And interval estimate, you just use a range of values and you estimate that your mean falls within these two values. And an interval estimate is accompanied by a specific level of confidence. It is called a confidence interval. So when you have got more confidence, it means that the interval is wider. And when it is less precise. But when you have less confidence, it means that you have a narrower interval, and it means that it is a more precise estimate. Now, when you take a sample, you say that I believe this sample comes from this population. Okay? So that would be the population of the general population. But then you look at the mean for your sample, and you might say, change your mind when you do the tests, and you might say that, oh no, I think the sample comes from this population or that population with a higher mean or lower mean. Now, estimate of a point estimate is the estimate of a specific value of a population parameter, and the best estimate of the mean of the population is the sample mean that has come from that population. And a standard deviation of the distribution of means is called a standard error and is a measure of the accuracy of that point estimate. Now here you can see that we have got estimation for the confidence interval, and the interval estimate with a given likelihood of including the population mean. So you say that I can give 95% confidence interval or 99% confidence interval, and that means that I'm 95% sure that my sample comes from a population that falls into these two ranges. Okay, so it means that if you take 100 times the sample, 95 times that sample mean falls within these two values. And the larger the interval, the greater one's confidence that the interval containing the true mean. Here we have got a normal distribution with a population mean of 220, and then we say that within 68% of my data falls within one standard deviation away from the mean. And here you can see I have put it as +1, +2, -1, -2, and that is your Z scores. 95% of the population falls within 2 standard deviation of the mean, and 99.9% of the data falls within 3 standard deviation of the mean. Sometimes it is necessary to estimate an unknown population mean based on the scores in a sample. So the best estimate of the population mean is your sample mean. So whenever I say that, what's the point estimate for this population, and I give you a sample, find the sample mean, and that would be the best point estimate. And we say that the sample mean is the point estimate of the population mean. And whenever you estimate a range of possible means that are likely to include the population mean, it is called interval estimate. And confidence limits are the upper limit and lower limit, or upper boundaries and lower boundaries of the confidence interval. So for the confidence interval, you always give me two numbers. Now, to find a 95% confidence interval, you need to find the cutoff points for the top and bottom 2.5%. And this leaves you 95%. So what do we mean by that? I have my normal distribution, and then 95% confidence interval means that this area in here, it takes 95% of the data. Okay, so if you find the cutoff Z scores for here, 5% is left. Okay, so if you do 5 divided by 2 is 2.5%. So this is 2.5%, and here is 2.5%. Yeah. So these two cutoff scores, you can find them from the SKI or tables, and it would be plus 1.96 and minus 1.96. All right. So in statistics, we cannot work always with rounding up, rounding down. We always go to 2 decimal places. So this 1.96 can't be 2. All right. When you calculate your confidence interval. You do for 99% confidence interval when the population standard deviation is known. We estimate the population mean by getting the sample mean and then figure the standard deviation of the distribution of mean. So whatever sigma was, you divide it by square root of sample size n to get the sigma of x bar. And then you find the Z scores that go with the confidence limits. And if you have 90% confidence interval, your confidence limit would be 1.64 standard deviations away from both sides of the mean. 95% confidence interval is 1.96, and 99% confidence interval is 2.57. Then you convert your Z score to the raw scores. And how do we do that? Multiply by sigma of x bar, not sigma of x, and then plus mean, mu. You remember that it was Z is equal to your value x bar, then actually we want the opposite way. We want the x's. So we say x is equal to your values of Z, whatever confidence intervals you are doing. If you're doing 90% confidence interval, you put your Z value of 1.645, whatever you want, multiplied by sigma of x bar and plus mu. All right, so once you do that, you get the two upper and lower limits for your confidence interval. Now, confidence intervals sometimes used instead of or alongside ordinary hypothesis testing. And if the confidence interval does not include the mean of the null hypothesis, this is very important sentence, null hypothesis distribution, then the result is statistically significant. So your hypothesized mean was outside your 95% confidence interval. It was not included in the confidence interval. And it is rare for researchers to know the characteristics of the population distribution, so to know the population standard deviation. But when they do, the hypothesis test that is appropriate is a Z test. Because our next step is we are going to talk about t-test. And t-test is done when the population standard deviation is not known. The alternate interpretation of confidence interval is that they are a region that depends on a sample that has a pre-specified probability of containing the true parameter value. For example, if we construct 95% confidence interval, then 95% of the times we perform the experiment, the interval will contain the straight confidence interval, and ESK refer to your computer lab file. Thank you.